Well, hello, class. We're here for the second part of the lecture today. And today, for this part, we're finally going to travel outward from Earth, and we're going to talk a little bit about the size and scale of the cosmos. So we need a setting to do that, so here we are today. Okay? So let's get started. So I have a few slides I'll show you here, and we can use this moment to explore the universe. If I can get the screen shared there. Okay, so the scale of the cosmos is one of the biggest challenges we're going to have when we start talking about the search for extraterrestrial life. The absolute easiest way for us to discover life is to go out and to look for it directly ourselves. But there are many challenges that prevent us from doing that, not the least of which is it's hard for humans to survive anywhere except the Earth. We need spacesuits and snacks and all of that sort of stuff. But the real problem, the real difficulty, as we'll discuss today, is the overall scale and size of the universe. Okay, so to talk about that, I want to talk a little bit about speed. This is the very first bit of quantitative calculation that we're going to do. So we'll do a little bit of that today to help us understand distances. We'll use this repeatedly throughout the course, so it'll be good to do it here early and start practicing. We'll talk about getting around the solar system, and then right at the end, we'll talk about jumping all the way up to the scale of the galaxy, which is where we're going to do most of our searching for extraterrestrial life in the future. Now, the first thing to remember about this is that our intuition that it's very hard to get to space is certainly well-founded, but it's also a bit of influenced by the fact that my and your everyday lives don't normally involve going to space. But in fact, space isn't very far away at all. So this is Fred Hoyle. He was a very famous English astronomer, and he once remarked that space isn't remote at all. It's only an hour's drive away if your car could drive straight upward. Okay, and so what he means by that is that the top of the Earth's atmosphere is where space begins. And in this case, the top of the Earth's atmosphere being an hour away is a statement of how high you have to go. There's a level above the surface of the Earth called the von Karman line, where if you cross that line, then you get your astronaut wings, and it's just about 60 miles over our head. Okay, so this statement is one that should not surprise you. Not surprise you in the sense that you should know how long it takes to get to space driving in your car if I tell you how far away it is. And that's because all of us have a lot of practical experience doing conversions between time and distance and speed when we're talking about your car. Your car drives at 60 miles an hour. How long does it take you to go 120 miles? It takes you 2 hours. If you have to drive for 15 minutes and you go 10 miles, how long does it take you to go 40 miles? It takes you an hour. Okay, so this is the way you do things in your head. You've kind of trained very well to do that over the course of your life, but there's actually a nice quantitative formalism to do that. That will let you extend this to virtually any case that you want to talk about, which is what we want to do. We want to talk about exploring the universe in the large. Okay, so if you go back to your original physics class, you will remember that speed, time, and distance are related in the following way. Speed is equal to distance divided by time. Now, if you've never taken physics or you've never seen that formula written down, it's in the way you talk about it. How fast are you going? What is your speed? Your speed is 60 miles, a distance, divided by a time, hour, 60 miles per hour. Okay, so the language you use, the statement you make, kind of has the formula hiding in it. Now, I've written it there in words, but of course, for manipulative purposes, it's convenient to write it in formula form. And so this is the common symbols we'll use. We typically use speed for v, which is velocity or speed. We'll use d for distance and t for time. Okay? Now, if you take this one formula and you just do a little bit of algebra, you can turn it into a formula for distance. Okay, so distance is just how fast you're going for how long you traveled. I'm traveling 60 miles an hour. How far can I go in 3 hours? 60 miles an hour times 3 hours is 180 miles. Okay. And so again, if I write that in formula form, I could just take that v equals d over t. I do a single algebra step and I get that d is equal to v times t. Okay. I can take this representation and do a little bit more algebra. And if I get time all by itself, then time is distance divided by speed. And also I can represent that in a standard algebraic form as well. Okay, so these are all exactly the same mathematical equation. They're exactly the same mathematical information. I've just written them down in 3 different ways by doing a simple algebra step between each one. So usually what we as physicists would do is we would not remember all 3 of these formulas. We just remember the one on the top there. And then if I need one of the others, I do the algebra step to get to the other one. Okay, so that's kind of what I'll exhibit doing every time we use these formulas in this class. Now we want to talk about traveling through the solar system, and we know all the distances in the solar system. Okay, and what I want to focus on for our discussion today is how long it takes us to get around. Okay, because that's the primary challenge to exploring the solar system. If we want to go somewhere to look for life on Mars or on Europa or on Enceladus or wherever we want to go. Okay, so we're going to use that last formula. So if I know distances and I know speeds, then I can compute the times it takes us to get there. Okay, so we need to know some speed. So how are we going to get around the solar system? Well, most of us explore the world by automobile every day. So the most common practical speed that any of us have is the speed you get in an automobile. Okay, and for those of you who have had previous physics classes with me, you know my favorite car in the world is the Yugo. So this is a Yugo. We are kind of using our imagination and speculating wildly, as we said last time. So we will imagine that a Yugo can go 60 miles per hour, okay, which is about 100 kilometers per hour. Okay, those of you who don't know anything about Yugos, you should go watch the movie Drowning Mona with Danny DeVito. It's great. Okay. The fastest that any of us have ever traveled is likely on a passenger jet. Passenger jets are about 10 times faster than the car, so they go about 600 miles per hour or about 1,000 kilometers per hour. Okay, so we can use these 2 speeds in order to ask ourselves, if we travel at the common speeds that humans are used to traveling, how long would it take us to travel around the solar system so that we can set up all the experiments we want to do to look for extraterrestrial life? Okay, so I've picked just a couple of destinations here. Okay, so just getting to Earth orbit, that's a little bit higher than getting your astronaut wings, but getting to Earth orbit, getting to the moon, which is the farthest any human has ever been from Earth. Okay, getting to Mars, where we've sent plenty of space probes, and certainly humans would like to go someday, and also getting to Pluto. And some of you may remember that we just visited Pluto for the first time with the first human spacecraft ever sent that far out to a distant planet, and that was New Horizons just a few years ago. Okay, so if I want to just get to Earth orbit, it's about 350 kilometers over our head, and traveling in a car, it would take you about 3.5, a little bit more than 3.5 hours to get there, or traveling in a passenger jet, it takes you about 22 minutes to go about that distance. Okay, so that's not too fast, too bad. Getting to orbit in ordinary kind of times, it's kind of like a half-day road trip, or like, you know, final approach as you're flying into O'Hare when you're coming into Chicago. Okay, so getting to orbit, no problem. The moon, however, is quite a bit farther away. The moon's 375,000 kilometers away. So if you and I got in the car and we started driving, and we didn't stop, we traded off driving, I drove while you slept, you drove while I slept, right? It would take us 5.4 months solid driving just to get to the moon. Okay, so if we had started at the start of the school year, October, November, December, January, February, yeah, we would have gotten to the moon just about 2 or 3 weeks ago. Okay, so the moon is really, really far away. Even traveling in a passenger jet at 600 miles per hour, it would have taken you more than 2 weeks to fly from the Earth to the moon on a passenger jet. Okay, So the moon, we think of the moon as being our closest neighbor. It is our closest neighbor in the universe, but it's pretty far away by any human standard. Okay? So what about Mars? Mars is the closest planet to the Earth. Okay, so it's about 1.5 times the distance from the sun as the Earth is. Okay, so it's about 90 million kilometers away. Okay, and to drive 90 million kilometers in our car, it would take 106.5 years. So as long as we took really healthy road trip food and we started right when we were little babies and we lived to be over 100, we would be able to drive from Earth to Mars. Okay. Now, I don't know about you. I eat lots of cheeseburgers. I don't know if I'll live to be 106, so I got to get to Mars faster than that. So I'm going to take the jet instead of the Yugo. Okay. And in a jet, it'll take 10.6 years. Okay. It would take an entire decade to get from Earth to Mars. So if you started when you were in second grade, you climbed on a jet and started flying to Mars, then you would get there by the time you graduated from high school. Okay, so Mars is pretty far away. What about Pluto? Pluto is the most distant. We'll argue some other day about whether or not Pluto is or is not a planet. It is, okay? The most distant planet from the sun. It's 5.5 light hours from the sun, or it's 40 astronomical units, 40 times the Earth-Sun distance from the sun, or traveling at the speed of light, 5.4 hours. If you got in your car and you started driving to Pluto, it would take you 6,900 years to get there. Okay, so basically, if the ancient Egyptians had started driving towards Pluto in their Yugo, they would just be getting there today. Okay, in a jet, it takes about 1/10 the time. It'll take about 690 years. Okay, so if we had left in the Middle Ages, we would just now be getting to Pluto. Okay, so the solar system, not even the entire universe, is enormous. It's huge beyond our ability to comprehend in the ways that you and I are used to. We think about distances and the time it takes us to fly around the world in an airplane or drive across the country in a car. But even talking about the closest part of the universe to us, our own backyard, our own solar system, it's enormous. Okay, and we'll come back to this question at the end of the term when we talk about, well, we'll come back to it before when we talk about sending space probes to look for life on other worlds, but we'll talk about starships at the very end of the term and talk about this table one more time. So there are many ways that we try and hold a mental model of the size of the solar system in our heads. Okay, and so a timetable like the one that I just gave you is one example. Many of you have seen models of the solar system that you could walk stretched out along parks or along the sidewalks in front of Northwestern. Sometimes the student groups draw them like that. But this is another model that you can use. And if we were in class together, I would encourage you to do this. So if you have the gumption, I would pause the video right now and go get yourself some paper. If you have a piece of calculator paper, okay, a piece about 4 feet long is good, okay, about the width of your arm stretched out from one end to the other. If you don't have any calculator paper, then if you just take an ordinary sheet of paper and you cut it into strips long ways, 4 strips, and then you just tape them to end, then they'll be about the right length to make this a useful exercise, okay? Okay, so how do we make this model? So the first thing you do is you take your piece of paper and on either end of it, on one end you draw the sun, and you probably can't see it there on my right, so there's my sun, okay? And on the other end, you draw Pluto, okay? So the length of this paper is the size of the solar system. It's 40 astronomical units from the sun all the way out to Pluto, okay? So take your paper, put Pluto on your sun, and fold the piece of paper in half, okay? And make sure you crease it, because by creasing it, you're basically marking the paper, okay? And then at the crease, that is the precise location of one of the planets in the solar system. So what planet do you think is exactly halfway between the sun and Pluto? Okay, well, as it turns out, it's the planet Uranus. Okay, now that should freak you out, because when we talk about Uranus, we talk about it being in the quote unquote outer solar system. We talk about it like it's way out in the boondocks, but it's really in the exact middle of the solar system. It's not way out in the boondocks. It's not all the way out on the fringes. It's in the middle. Okay? Okay. Now, if you take Pluto and you fold it toward the crease where you just marked Uranus and make a new crease, okay, then on that new crease is the planet Uranus. Okay? So the outer solar system, the outer half of the solar system, not the outer 1/10 of the solar system, not the boondocks way far away. The outer half of the solar system only has 3 planets in it: Neptune, Uranus, and Pluto. Okay? Now we're going to work with the other half of the solar system. Okay? So if you take the piece marked Sun and you fold it to the middle of the paper, which is where you marked Uranus, and make a crease, then the planet that appears at that crease is Saturn. Okay? And if you take the Sun and you fold it now to where you marked Saturn and make a new crease, then the planet that appears at that new crease is Jupiter. Okay? Now look at your piece of paper. From Pluto to Uranus is the outer half of the solar system. Okay? If you fold between Uranus and the Sun in half, the location of Saturn, you're a quarter of the way from the Sun to Pluto. So Saturn is in the inner 25% of the solar system. It's the boundary of the inner 25% of the solar system. It's not really far away either, but we still talk about Saturn as if it's in the outer solar system. Jupiter is at half the distance between Saturn and the Sun, so Jupiter is only 1/8 of the distance from the Sun all the way out to Pluto. Okay? Jupiter is where we normally start talking about the outer solar system. So 7/8 of all the space in the solar system, from Jupiter all the way to Pluto, is what we normally call the outer solar system. Okay? But it's actually most of the space in the solar system. Okay? So if you take the Sun and you fold it to Jupiter, that gives you the location of the asteroid belt. And if you fold the Sun to the crease you made for your asteroid belt, that gives you the location of Mars. Okay? Now the last fold is the most complicated. Well, it's not complicated, it's just different. Is you fold the Sun over to Mars and then don't unfold it, then just fold that little bit of paper over to Mars again. And what that does is that will make 3 creases in your inner solar system. And those 3 creases mark the location of Mercury, Venus, and Earth. Okay? So if you've done that and you've followed along and you've marked every mark that we've had, you should now have a scale model of the solar system. Now, the beauty of this is that we didn't make any measurements at all. We didn't get our rulers out. We didn't get a calculator and a spreadsheet and look up the distances to the planets and calculate what they should be on this scale, okay? The reason this works is there's a very old observation about the solar system that the planets are spaced in a regular way. That is usually called the Titus-Bode pattern. It used to be called the Titus-Bode law. We used to think there was some significance to it, but it's just a consequence of the way the planets formed and migrated during their formation. We'll talk about this when we talk about exoplanets, and the solar system just happens to be in that state right now. And as it turns out, the Titus-Bode pattern is very close to the exact spacing you get by folding the paper the way we just did. Okay? So here's a complete picture, which you can see in the slides, which I'll post online, that shows the pattern of folds you make. So starting from the right side of this picture, you make the first fold, the second fold, third, fourth, fifth, along, and marking them as you go along. And then eventually you'll have your full scale model of the solar system. Okay? So that's the solar system. So if you lay this out on your kitchen counter or in your hallway, this is the beginning of a scale model of the entire universe. So the natural question to ask is, if this is our solar system, then where should I put the nearest star to the sun? So the nearest star to the sun is Alpha Centauri. And as we said last lecture, it's 4.3 light years away. Okay, so on the scale of our little piece of paper for the solar system, how far away is 4.3 light years? Well, 4.3 light years is about 52 miles away. Okay, on the scale of your little 4-foot long piece of paper, okay, 52 light years is, or sorry, 4.3 light years is 52 miles away. So if you're in Evanston, and if we were doing this together in classroom, we'd be on campus at Northwestern in Evanston, then that would mean that the nearest star would have to be out somewhere on this red circle that I've shown in this picture. So if you went due north from Evanston, it would be somewhere in the city of Racine, Wisconsin. If you head, southeast, then it'll be over in Indiana in Michigan City. Okay, so the nearest star is far away. And the important thing to remember about that is that when we look at the solar system, okay, most of what we just drew on this piece of paper is empty space, okay? But between the sun and the nearest star, there isn't anything else. It's the nearest star. So everything inside that circle is completely empty, except for the little sun that you drew on your little map sitting there at the dot in downtown Evanston. Space is really empty, and it's really huge. It's really big. It's gigantic, which is why searching for extraterrestrial life is going to be so hard. Okay? We don't have to stop at the stars. We can jump to the center of our own Milky Way galaxy. Okay, so the center of the Milky Way galaxy is 24,000 light years away. Traveling at the speed of light, it would take you 24,000 years to get there. Okay, and on the scale of our map that we just made, where Alpha Centauri is up in Racine, Wisconsin, then the center of the Milky Way we would have to put down on our map at a distance that's 50,000 miles past the moon. The galaxy is enormous, right? And already you can see that our model is making our brain have problems, right? We'll say, okay, well, the center of the Milky Way is 50,000 miles past the moon. The moon is enormously far away, and on the scale of this model, right, it takes you and I in our car a long time to drive there, 5.5 months. And we have to go 50,000 miles farther in order to locate the center of the Milky Way on our little paper model that we've made for the cosmos. Okay, the cosmos is enormous beyond our way to normally understand. Okay, on this scale, if I wanted to put the nearest galaxy to us, so the nearest galaxy to the Milky Way that's similar to it is called the Andromeda Galaxy. It's 2.5 million light years away. Traveling at the speed of light, it'll take you 2.5 million years. If we want to put the Andromeda Galaxy down on our little map, it would be almost all the way to the orbit of Mars. Okay? And the Andromeda Galaxy really isn't that far away in the total context of the size of the universe. Okay? The universe is a ginormous place. Okay? And this paper model, just like our table of travel times, is a model that we've made to try and help us understand exactly how ginormous it really is. Okay, and it's hard. Okay, there's just no easy way around it. So what should you learn from all of this? So the first thing, which we said a moment ago, is that the solar system is mostly empty space. Okay, so that's good because it means we can pretty much fly wherever we want to go and not have to navigate around anything that's in the way. But it means that there's a lot of nothing in the solar system. Okay, so it means we can easily know where to look because we kind of know where all the planets are and where all the moons are. But that lot of nothing extends not just to the solar system, it extends to most of the cosmos. And so looking for life is all about looking in the right places, and we got to find the places to look. Okay, and that's really all about finding planets, and we'll talk about that in a little bit. Even the hard places in the solar system are really hard to get to. On the scale of our map, okay, you'll remember that the Earth is way down here, very close to the sun. On the scale of this map, the distance between the Earth and the moon is about the width of the lead in your pencil. Okay, and the moon is the farthest humans have ever been from the Earth. Okay, so we haven't even been even to the close places in the solar system, and getting to even the close places in the solar system is going to be hard because it took us 4 days to fly from the Earth to the moon using the Apollo rockets. Okay, so getting anywhere else is really, really hard. Okay, and then the other thing that you should learn from this picture here is we got our little 4-foot long map of the solar system there. Is apparently I'm pretty short. So, okay. Okay, so let's go back to this here, which is our distance. So I've added the center of the Milky Way and the Andromeda Galaxy to our travel times there. Okay, and we're going to travel to them eventually. We'll talk about this when we talk about starships at the end of the quarter. But driving in your car, it would take you 291 billion years to get to the center of the Milky Way, or 29 billion years to get to the center of the Milky Way in our passenger jet. Okay, now you can take those numbers, you can calculate them yourselves, just like I calculated them. But the thing that you may or may not realize, depending on how much astronomy you know, is that both of those times are longer than the age of the universe. Okay, so even if we had been flying for the entire 14 billion year history of the universe, we still wouldn't be there. Okay, and the Andromeda Galaxy on this scale is even farther away. It's trillions of years away at ordinary human speeds, which is way longer than the age of the universe. Okay, so what should we think of all of this? Well, I always, our brains are difficult to wrap around these kinds of ideas. It's easy to calculate the numbers, but it's very hard to imagine what they mean. And so just as we said in our last lecture, we're often going to lean on language to communicate. And I think in order to kind of understand the brain melting that you have when you think about things like this, I often fall back on language. And so I'm particularly fond of this quote from Carl Sagan. So Carl Sagan once said at the beginning of Cosmos, he said, "The size and age of the cosmos are beyond ordinary human understanding. It's far outside our everyday experience. Lost somewhere between immensity and eternity is our tiny, tiny planetary home, the Earth." And that's really where we're starting. We're starting on this tiny fleck, and we're trying to answer a question that the only way to answer the question is to explore that enormous nothingness that it's really so hard to wrap our brain around. Okay? So this is where we're going to start. This is the size of the problem that we're talking about. And so next week, we'll start with a different problem, which is let's talk about what life really is, what we mean when we say life, and how it is we're going to go looking for it in all of this immensity. Okay, so I'm going to end there. And I think that's all I have to say for today. I hope all of you are having a safe time and staying safe and well on your starships, wherever you are. And I'll see you next week. Take care, everybody. Hi, class. During our first half of the lecture today, we were talking about cognitive dissonance and the sorts of things that we're going to have to come to grips with. And one of the most difficult things in science is that when you make calculations and you do experiments, you interpret them, and sometimes you make mistakes, sometimes you interpret them wrong, and you have to come back to your problems and figure out where you went wrong, admit that you did things wrong, and then move forward. So in classic fashion, the universe has done this to me. And when I did our solar system model, when I extended the model outward to the parts of the cosmos outside the solar system, I made a factor of 10 error in the scaling factor. How it happened is an interesting story, but I'll tell you some other day. So the point is that the distances to Alpha Centauri, the distances to the center of the galaxy, and the distances to the Andromeda Galaxy were all said to be larger than they would on that model in the lecture video. I've corrected them in the slides, and they're correct in my notes. So on the scale of your paper solar system model that you made, to get out to Alpha Centauri, you would have to only go 5.2 miles, not 52 miles. To get out to the center of the Milky Way, which is 28,000 light years away, you would have to go, sorry, it's 24,000 light years away. You would have to go 28,800 miles, which is in high Earth orbit. And then to get to the Andromeda galaxy, which is 2.5 million light years, you would have to go 3 million miles away from the Earth. So that's about 12 times the Earth-Moon separation. Okay, so this will happen to you, certainly in your career. It happens to us in science all the time, and it absolutely happens to me in lecture, which is we will make occasional errors. When we make those errors, we're courageous about admitting that we made them, we make the correction, we go forward. So what you just heard in the video, those are the only 3 numbers that I think I got wrong. If you feel industrious, you can certainly do the calculations yourself and let me know if you get a different answer. Okay, so hope you're all having a good day. I will talk to you again soon.